So welcome. So we're going to talk about gravity today. And Newton was the person who did most of the stuff about gravity. And the story is kind of interesting. It's not that people didn't know about gravity. They just never thought to describe it mathematically. There was good old Aristotle, who his theory of gravity was that things that were made of earthly stuff had this longing to return to the earth. And so if it was made out of oil that you dug out of the ground and you let it go, it went back to the ground because that's where it came from. And if it was like smoke, it went to the heavens because air comes from above. So, and if you had more of it, you got more of a longing, so it went faster, which it turned out wasn't true, and so on. So it was almost like he looked at the world and he made up stories to explain stuff. But he didn't actually go that next stage and test stuff. And then historically along came Galileo, who tested stuff and wrote down observations. And then along came Newton. And Newton went beyond and started mathematically describing things. So Newton was a great physicist who was very comfortable with math. And so during the Great Plague, everybody was sent home because the universities were a hotbed of disease. 1666 thereabout. And Newton was sat in his family farm in Lincolnshire, and he was sat in his backyard, which was full of apple trees. And they say an apple fell on his head. Maybe it did, maybe it didn't, but he certainly observed apples falling. And the thing that he realized was that effect, that pulling of the apple and drawing the apple to the earth, was the same effect that held on to the moon. Now, the outcomes are very different. The apple hits the earth. The moon, as far as we know, does not hit the earth. And so it's tempting to say they're completely different. But what Newton realized was that the physics that controls the apple falling to the earth must be affecting the moon and the earth. And so the reason why it doesn't hit the earth is because of some other stuff. And it is the sideways motion of the moon that stops it from colliding with the earth. If we could stop the earth, just like we stopped the apple from moving sideways, the moon would fall into the earth just like the apple does. So he was able to see the big picture and say, if it works here, it works up there. Aristotle would have said the moon's sacred and divine and special and the laws are different. And Newton said, no, it's the same laws. So that was really the smart thing to do. And so what Newton said was, let me get my pen. What Newton did was he said, okay, Newton recognized that the force between the earth and a falling apple is the same type of force that pulls the moon in an orbit around the earth. And he summarized his work in the universal law of gravitation. Now, I swear I could cover this up and we could figure this out, because it's kind of logical what he did. He said, here's an object and here's another object. Let's call it M1 and M2. And then you used to ask yourself questions about it. You say, look, well, M1's pulling on M2 and M2's pulling on M1 because of the substance. It's because of the substance. So if I made M2 bigger, if I made M1 bigger, would I get a bigger force of gravity or a smaller force of gravity, or would it stay the same? What do you think? If I have more stuff doing the pulling, will I get a stronger pull? Yeah. If the force goes up, as the mass goes up, put the mass on the top. If the force goes up, because the mass goes up. The alternative is that it makes no difference. If it makes no difference, then I should be pulled just as hard by a small object as by a big object. And so my pen should pull me just as hard as the earth pulls me. We know that's not true. And the other alternative is that the force of gravity gets bigger as the mass gets smaller. In which case my pen should pull me even harder than the earth pulls me. Not the same, but even harder than the earth pulls me. And none of those things are true. So we can say, oh yeah, if the mass gets bigger, so the force gets bigger. And then we say, well, what about the other mass? Supposing I make the other mass bigger. What's going to happen? Either the pull of gravity gets more or stays the same or becomes less. And it's easy to see. It's not going to get less. And it's not going to stay the same. So it must be that M2 goes on top as well. And then the only other thing that matters is the separation. And so we play that same game and we say, well, if the force gets bigger as the separation gets bigger, then a book on Venus must pull me by a tremendous amount compared with a book on Earth. Pluto would pull me harder than the moon pulls me. The sun would pull me harder than harder than the Earth pulls me. So if I believe that as the distance gets greater, the force gets bigger, then the stars would dominate my life because they're a long, long way away. And so the forces will be really, really, really big. So that can't be. And it can't be independent of distance because there's a lot of matter in the stars, and so that would dominate. It must be that as the distance gets bigger, the force gets less. So D goes on the bottom. So we're almost there. Final little bit. So here's my M1, and it's having an influence around it. We call that the gravity field. It's a bit like the brightness of light. As you get further away, the light gets dimmer. As you get further away, the gravity gets dimmer, if you like. All the gravity effect, which goes through the first sphere, must go through the second sphere. But it's spread out a lot more. So it's got to be less intense. Just like the light going through the first sphere is the same light that goes through the second sphere, but because it spreads out, it's less bright. So the intensity of the light falls off with the area of a sphere. And we don't need to know it, but it's 4 pi r squared. So my gravity intensity falls off with the area of a sphere. And that's 4 pi r squared. So can you see how as my radius gets bigger, r squared gets even bigger, yeah? So this is not d, this is d squared, because it reflects my area effect. I'm almost there. I want an equal sign. How do I go? That, if I put proportional, the little fish down, that's right. That's Newton's equation. We just made Newton's equation up, and we don't get any credit for it. It's like, it's so upsetting. It's like, man, if I'd been born 400 years ago and known what I know now, except they wouldn't have taught me that in school. They'd have taught me what Aristotle taught, which was all wrong. But if I want to go from an equal sign to from a proportional sign to an equal sign, I put a fudge factor in. I put a number that makes the numbers work. And sometimes this has physical meaning, and sometimes it's just a number. Sometimes it's the number 1, because we got lucky and it works out. It's number 1. Sometimes it's 9 times 10 to the 9. Sometimes it's 32 times 10 to the minus 16. It just depends on the circumstances. Depends on your units. If you're using inches and pounds, you'll have a different G than if you're using meters and kilograms. But it's just a number. And Einstein and good old Newton had no idea what that number was. He knew it existed, but the only way you can find that number is by doing the experiment. And the experiment wasn't done for another 150 years. It was done by a guy called Cavendish, who built an apparatus in a room that enabled him to measure that value. And he got it really good. It was the most amazing thing. So, but the trick for us is when you look at equations, so whether you're going to become a mathematician or a physicist or not, you know, chances are you are going to see some equations sometimes and just recognize there's a certain pattern to them. The first term is always the most important. It's always the crudest terms. If there are second terms, they're refinements. And then there's always the things that affect the answer. And then there's often a fudge factor, which makes the equal sign work. And once you get them like that, you can deconstruct them. So G equals, turns out, 6.7 times 10 to the minus 11. Minus 11 is like a tiny bit. Newtons, meters squared, kilograms squared. This is such a small number, it takes a lot of mass for a body our size to feel the effect of gravity. If this were a bigger number, then we'd be pulled by a table. We'd be, if we had a couch, we literally would not be able to get off the couch because it would be pulling us so strongly. But it's a really weak force, so we can basically throw things through the air. And it curves back towards the earth, but it's not slam dunked into the earth. The value of G tells us that gravity is a very, very weak force, so we sense gravity only when we're near a massive object like the earth. I mean, think how big the earth is, and we can still jump away from it. We get dragged back, but we can jump away from it. I mean, it's huge. It's like 6,000 miles in diameter. It's a huge thing. It's actually something like 10 to the 31 kilograms. It's a massive thing, and yet we can jump away from it. So let's have a look. Where's my clicker? It's only this class where this happens. I was in here before. And I swear I've clicked something. I have clicked something. Oh, I know. I think I have clicked something. I'll sort it out. I swear I will spend half an hour trying to find out what I clicked. A mass of 2 kilograms is located 3 meters from a 4 kilogram mass. What is the force of gravity that is felt by the 2 kilogram mass? Notice I'm cheating. I'm leaving that big G in there because I don't want to mess with it. So I say F is equal to big G. I don't like M1 and M2. It really ticks me off. So I call it big mass and little mass so that I get an idea for it. D squared. And that's allowed. It's like, you know, there's no police. Like, if you want to put on your cap, but you call it a hat, there's no police saying, I'm sorry, but that's a hat. You can't wear it because you said cap. Okay? So there's no police saying you can't use big M and little m, or MA and MB, as opposed to M1 and M2. So don't get tied into the literalness of an equation. It's a shorthand. It's like a sentence. It's literally like a sentence. And so we can use different symbols like we can use different words to say the same thing. So there's our equation, but they do mean something, so we've got to know what it means. And I've got to visualize. So here's my 2 kilogram and here's my 4 kilogram. I like to put my mass numbers inside. And let's have a look. Is there a separation? 3 meters. So that's 3 meters. So I like to visualize. And then I just plug and chug, to be honest. I just go, well, G's not affected. The big M is 4. The little m is 2. And that's going to be 3. And it's got to be squared. So that's going to be F is equal to 8 over 9 big G. And I think if you work that out, that's 0.88 big G newtons. I still need the units. That tells me it's a force. This is just a number. So don't be put off by that. Okay? I don't want you to have to figure with these weird numbers. I can teach you the science just leaving G as G. So some people feel uncomfortable with that, but I can. What is the force of gravity that's felt by the 4 kilogram mass? Oh, hold on. Well, hold on. That would be G big M, little m over d squared, which equals g. Oh, it's the same problem, isn't it? It's the same separation, the same two masses, so it's going to be the same answer. And we knew that, didn't we? Because we knew that action-reaction pairs equal and opposite. So the force of the 4 on the 2 is the same as the force of the 2 on the 4. So that's Newton's third law again. So again, it's going to be that. And we could have just said Newton's third law. You know, I'm done. So this is a little bit about... so I'm imagining a mass. And I'm saying, well, here's one distance from that mass, and here's another distance from that mass, and here's another distance from that mass. It's spherical because it goes out in all directions. And I'd like to know the pull of the force of gravity, the weight, on an object at these different positions. So I say we can understand how gravity is diluted. I'm using that word for want of a better word. I could say, I don't want to say weakened, although it is less intense would be a good word, a good 2 words. We can understand how gravity becomes less intense with distance by considering how paint covers the outside of a sphere. This is known as the inverse square law. If I take a can of paint and I put it on on a table tennis ball, it will be quite thick. If I put it on a softball, it will be less thick. If I put it on a basketball, it will be less thick. If I put it on a beach ball, it will be less thick. So I can, same amount of paint, less thickness, because the same amount of volume gets spread out over a larger area. So we say for gravity, we can represent this graphically. The distance term is between the center of the gravity of the two masses. Oh, I see, okay. So I'm imagining, let's make that a bit bigger. I'm imagining that mass there and a mass there. And so my R is that guy. And I'm saying, so what happens to this force as the distance increases? And what we say is the distance term is between the centers of the two masses, and no matter what the distance, the force of gravity never actually goes to 0. That's a frightening thought. If I go like that and move some mass away from Pluto, Pluto gets pulled a little bit towards us. Well, a tiny little bit towards us. It's like unmeasurable. But in principle, it had an effect on it. Doesn't ever go to 0. But it gets so close, it does not matter. That's the key point. It does not matter. 60 kilogram person. So if I plot it, if that's, let's say that's 16 newtons, and that's 1 meter. Here's a trick I want to show you. That's 1 meter. This goes as the inverse square law. If I double the distance, it's not half the force. That's the inverse law. It's the inverse square law. If I double the distance, sorry, just notice this. If I double the distance, then I quarter the effect, because it's inverse square. 1 over the number squared. So if that's 2 meters, 1 over 2 squared is 1/4. A quarter of 16 is 4. If I triple the distance, that's 3 meters, it's 1 over 3 squared. 1/9 of 16, I have no idea what that is. It's something, 1 and a bit. If I 4 times the distance, then it is not 1/4, but 1/16 of the effect. Oh, 1/16 of 16 is 1. So there's a really specific shape to this. It goes, as you go from 1 to 2 to 4, you go from 16 to 4 to 1. And so on. So there's a real specific shape. And we play with this so much in the physical world that we get quite familiar with it. 60 kilogram person, that's about 120 pounds. If you want to know kilograms in pounds, basically you double it. So a bag of sugar, 2-pound bag of sugar is about 1 kilogram. So So picture a bag of sugar and think that's a kilogram, it's 2 pounds, it's a kilogram. So think of it like that. So if I'm at 60 kilograms, I'm 120 pounds. Will weigh, because of the pull of gravity, 10 newtons, little g equals 10 newtons for every kilogram. So 60 kilograms becomes 600 newtons at sea level. But if I happen to be on top of the tallest mountain in the world, I won't be 3,000 miles from the middle of the earth. I'll be 3,005 miles from the middle of the earth. It's not really 3,000, but it's close enough. I'll be 5 miles further away because it's 5 miles up in the air. And so the pull of gravity will be a little bit less because of this inverse square law. I'm a little bit further away, and so there's a little bit less force. So rather than 600 newtons, they estimate I would be 598 newtons. Right, interesting, 598 newtons, just that little bit further away. So if you go into the space station, this is going to be an interesting question, actually. If I go into the space station, if I went as high as the space station, and there was a platform there, and you put a set of scales underneath me, I would have a weight because the Earth is pulling down on me. But people in the space station, if you put a scales at the bottom of the space station, would not record a weight. So we say they are weightless. But that's not because of their position above the Earth. That's because of their motion. They are falling. It's like if you stood in an elevator. Well, if you had a drink and you jumped off a diving board, when you first jumped, the drink would kind of slosh up a bit, wouldn't it? But as you fell towards the water, would the water be left? Would the soda be left in the air like on a cartoon, or would the soda be in your cup? It'd be in the cup. If you jumped off a diving board and just let go of the cup, it would just like fall with you, wouldn't it? So, if I measure weight by pushing down on something, which is how we measure weight. We kind of like stand on a scale. And me and the weight are falling at the same rate. I can't push on it because it's always moving away from me. So I developed this term weightlessness, and it does not mean to say there's no gravity pulling on me. It means to say that I don't record anything on a scale. And it's not because there's no gravity. It's because there's a motion. There's this satellite motion. We'll talk about that. I kind of got a bit ahead of myself. So. Mass X is located y meters from mass Z. Mass X feels 12 newtons force of gravity. So let's visualize. Mass X, Z. That is y meters. Are you feeling uncomfortable about the letters? Most people do. They feel uncomfortable about the letters. What is the force of gravity? Oh, yeah. So, mass X feels 12 newtons. Now remember, the force of gravity equals big G, big M, little m, over r squared. What's the force of gravity that is felt by mass Z? What's that force? What do you think? Just somebody say it to me. If that's 12 down, The force, yeah, the force of the z on x is equal and opposite to the force of x on z, so that's going to be 12. That's just Newton's third law. What force of gravity would be felt by x if the separation between the two masses was doubled? When I double the separation, it's an inverse square law, I get a quarter the intensity. So it was 12. So what would it be now? 3. What force of gravity would be felt by x if the separation between the two masses was tripled? 3 times 3 squared is 9. 1 over 9 times 12. 1.33, I think, yeah? So I'd like you to be comfortable with, if you times 2 the sep, 1/4 the force, times 3 the sep, 1/9, times 4 the sep, 1/16, times 5 the sep, 1 over 25. Just get used to that pattern. It'll keep coming up. It's in sound, it's in light, it's in gravity, it's in electrostatics, it's even in magnetism, which is a bit surprising. So let's get to this thing about weight and weightlessness. The weight of an object is the force it exerts against a supporting floor or another object, like a scale. Weightlessness is not gravitylessness. Your weight depends upon your situation. So you are weightless when you fall off a cliff. If you had a scale under you and you looked down, if you said, oh, I don't care about the ground, I'm going to see what I weigh, it would read 0. But you've still been pulled by gravity. So you're weightless, but you're not gravityless. Okay? Gravity's still pulling on you. That's why you're going towards the ground. If I put you in a can and I accelerate you into space, well, not into space, but let's say through interstellar space, there's no planets anywhere. You're in the middle of the void. And I put you in this can and I keep accelerating you at 10 meters per second squared. It feels to you like you're on the surface of the earth, because that's the pull of gravity. And so you have weight, because if I put a scale under you, it will read your weight. But you are gravityless. So no gravity. So I can cheat. I can make gravity appear by accelerating. Has anybody seen? There's a famous science fiction. There's a famous science fiction film called 2001: Space Oddity. I think it's like that. Odyssey. And it's by Stanley Kubrick. How many people have seen it? Okay. It's worth looking. It's on Netflix, I'm sure you can find it somewhere. It's like the first, I think of it as the first really good science fiction movie, because of the special effects and the like. And it's a very strange movie. The principle is there's aliens who basically are bringing on human beings, or at least monitoring our development. So there's a bit where our primordial ancestors, this stone appears and they touch it and it affects them. There's a big communication, and they invent tools for the first time. So they go from being animals that just live to animals that do stuff. And then the next thing is they're exploring the moon. When this was brought out, it seemed like we might explore the moon and then we just stopped going there. But we had mines on the moon, and they discovered this stone on the moon, and they touch the moon, and there's this zap of inspiration, and it comes from Europa, one of the moons of Jupiter. So they go on this quest to Europa. And I won't tell you the rest of it because I don't understand the rest of it. It gets a bit weird, actually. But it's just amazing in terms of the technology, because some of the technology is we know, like the computer displays look pretty crude now, But at the time they were like, wow. I remember thinking, wow, they got this 3D picture and it's moving. It's like, I couldn't do that on our computer. On our mainframe, we couldn't do that. No, I'm sure some people could, but we couldn't do that. So it was this amazing portal onto the future. And there's this bit in space, and what they do is they have this space wheel, and it's basically this structure where it spins. And what happens is people can walk around on the outside of it, on the inside of the outside, and because of the spin, it feels like there's gravity. And so they're in space, but they're not gravityless, and they're not weightless. So they can have a normal life, but they only go in circles. And it turns out that the reason why we've never built one is that the human body gets uncomfortable when we have more than 1 rev per minute, I think. If we go faster than that, then we start throwing up and we just don't do well. And in order to make this work and get the right acceleration, it has to be something like 2 or 3 kilometers, about 1 mile or 2 miles in diameter. And so it's just so expensive to build it. You could make a smaller one, but it'd have to spin so fast, you'd be like throwing up all the time. But so they did that. So true or false, when you are falling down an elevator shaft, you are weightless. If you had a scale underneath you, it wouldn't read anything. But gravity does act on you. What do you think? That's true, isn't it? And then true or false, when you are accelerating through interstellar space, you have weight because you're accelerating, but gravity does not act on you. That's also true. Almost there. Oh, no, okay. Next time. Ocean tides. And what I will do is I'm going to sit here for a while, and I will try and sort out why I can't get this thing to look like the other computer and the other class on this side. And if somebody came in late and you want to get your Scantron, I've got your Scantrons here. And if you didn't pick up your old tests, I've got some old tests. And I'll see you guys. Oh, yes. So don't come to class next week, okay? And have a good, restful weekend and be safe and just enjoy yourself. Thank you. It should be there. Oh, you mean the Scantron? You mean the Scantron. So it's probably, unless I squirrel it away somewhere, it's in this stack. So let me have a quick look. So let's have a look. Eugene Wynn. Yes. There you go. Thank you. Yeah. Kevin. Oh, yeah. So, Bonaquisti, what is going on with this? This is like... Oh, I better do this. Not now.